So in this problem, we have a turbine and the inlet conditions for the turbine is given the pressure and the temperature, and also the outlet conditions for the turbine is given pressure and temperature. We have the flow rate through the turbine given in kilograms per hour. This is important to note. It is in kilograms per hour, not our usual units of kilograms per second. So we have to be careful when we are using these units. And then this turbine has some heat loss given here in kilojoules per seconds. And we have to remember kilojoules per seconds is equal to kilowatts. And we are asked to calculate the power output from the turbine. In a question like this, we have to consider the energy balance and the mass balance. Both of these are considered in rate form in this case. Let's start with the rate mass balance. Let's start with the mass balance. And we know that in these steady state systems, change of the mass within the system is going to be equal to 0. So we can write this equation. Instead of calling them m in and m out, the mass flows in and out, let's call both of them as m dot. In our energy balance, we know that Q and W is not going to be 0 because Q is given and we have to find W. But this is a small device, so GC and GC in the inlet and outlet cancels out. And we can neglect the kinetic energy changes because there are massive changes in enthalpy, heat loss, and work output. And we know for a steady state system, energy change within the system is going to be 0. So we can rewrite our energy balance equation as such. Also, it is important to note that we are using the energy balance equation in the form of formal energy balance equation. So heat coming into the system is going to be positive and work coming out of the system is going to be positive. That is why we have a negative heat output, and work output we consider it as positive. We can solve this equation to find W out, but we have to find HI and HE values. Now the pressure and the temperature of the inlet is given, and first we can assume that the system is superheated because we have to find properties using temperature and pressure. And let's go into 4 megapascal pressure table. This is water, and we go to 4 megapascal pressure table, and in front of 500 degrees Celsius we have the enthalpy that we need for H in. Similarly, we have the pressure and temperature for the outlet, so we are going to assume that it is going to be superheated tables, and we go into the given pressure table under superheated water, and in front of 250 our temperature we have this enthalpy, so that is the HE. Now we can substitute all of that into our previous equation that we solved for W, and we can get this equation. Here we have to remember that our flow rate m dot is in kilograms per hour units. So we are going to multiply that with the unit conversion ratio given here. 1 hour is equal to 3600 seconds. So 1 hour divided by 3600 seconds is going to be equal to 1. So we can multiply that. We can use that to multiply anything without any changes. And we have the HI that we found and also HE that we found. And simplifying this gives us the W out value to be 156.68, which is very close to answer A. So answer A is going to be our solution for this problem.